Rolling. Thanks for joining us today. This is the third of 4 webinars that Griffin is presenting to New York cannabis license holders. The rules and regulations in New York around some things like lighting are a little different than in other places. We've talked in previous sessions about infrastructure, lighting, and we've presented a model for a ground-to-ground house that can be expanded to have multiple houses that we think is a really great starting point for folks in New York. Today, we're going to shift away from equipment and infrastructure and start talking more about what the plant needs. Today, we're going to hear from Erica Hernandez, CEA's GGS Pro Technical Specialist. She's going to walk you through crop nutrition for cannabis. So she's going to talk about why the crop needs what it is, what the different nutrients do for the plant, and then she'll take you at the back side of the talk through some basics on the fertility program that works well for cannabis. We work with growers across the country. We've got a lot of experience in what the crop needs, and so you can trust that the information you're going to get from Erica today is very sound. So with that, I'm going to turn it over to Erica. Erica, thanks much for being with us today, and thanks for sharing your knowledge with the group.
All right, thank you so much for that intro, Tammy. So we've got a lot to cover today, so we are just going to dive right into it. If you have any questions, please feel free to put them in the Q&A panel. And Tina today will be our moderator, who may stop me at some point or another to ask questions, or we will have a Q&A session at the end. So let's dive in. Crop nutrition for cannabis. So what we're going to cover, Tammy gave you a little bit of an intro. We're first going to talk about nutrients, a very basic level. We want to take you from the basic understanding of what plants need in general and put that into a cannabis perspective. We're going to talk about fertilizers. So where are those nutrients coming from, and how do you understand the many different products that are out there? And then we're going to end up on water quality and fertility. So understanding your water quality and how it can contribute to influence your fertilizer plans that you come up with for cannabis. All right, starting off basic, the essential elements. There are 17 essential elements that plants need, all plants need, to complete their life cycles. And, you know, this is going to be something that we might talk about with any living organism. Humans have essential elements that they need to survive, so do plants. And with plants, they can all sort of be organized into this pyramid. We will go over this step by step. So this is a lot of elements, but you don't need to worry about all of them all the time. Let's break it down a little bit for you. At the very bottom, we've got our basic nutrients. Now, these are nutrients that are not provided by soil or fertilizer. These are coming from the environment. And when you look at what they are, it makes sense. We've got carbon, we've got hydrogen, and we've got oxygen. So these elements are coming from the air in terms of, we are breathing in oxygen. There's oxygen in the atmosphere. They're coming from carbon dioxide, which also is in the atmosphere, but also many growers may supplement that in their facilities. And hydrogen also coming from air, from water, from the soil. So these are things that you don't have to think about providing, but they are very basic and very foundational for any organism. With oxygen, we're using that in cellular respiration to break down sugars for energy. So that's a very low level, but very important activity. For hydrogen, we're using this to create sugars and to store and move energy around our plants in our biological system. Very low level, very important again. And carbon is a key component of pretty much any sugar. And carbon fixation happens when we're building those sugars and plants are storing that energy during photosynthesis. Again, these are very foundational, very critical, and they're things that just happen in the background as part of a living organism. So very basic there, but moving on to things you can control a bit more, primary and secondary macronutrients. In the second and third level of the pyramid here. Now, these are things that you will hear people talk about quite a bit when it comes to fertilizers. So when you hear somebody say NPK, when they're talking about a fertilizer, they're usually talking about nitrogen, phosphorus, and potassium. These are our primary macronutrients. That's how we would refer to them. And these are elements that are required in relatively large amounts for plants to complete their life cycle. Plants need nitrogen, they need phosphorus, potassium, but then we also come to the second category here, secondary macronutrients. These are needed in slightly less amounts, but still very, very important on a high level. The calcium, sulfur, and magnesium category. So these are where the meat and potatoes of our fertilizer plans are going to happen for the most part. And then finally, at the top of the pyramid, we've got our micronutrients and our beneficial elements. Now, just because things are needed in very small amounts doesn't mean that they're not needed at all. Micronutrients are still very much required for completing plant life cycles. And people may refer to micronutrients as trace elements, and these are going to be things like boron, copper, iron, very popular, very problematic element at times, and we'll discuss some of these issues. Manganese, molybdenum, nickel, zinc, chlorine. So those would be considered micronutrients that are required. But there's another second category here, which are beneficial elements. These might not be required for all plants universally, but they're good to be aware of. In terms of, what are these used for? Micronutrients and beneficial elements are typically important for chemical processes that are going on, but they're not usually incorporated in structural things that are happening. They're not usually actually incorporated into sugars. They're not in like plant cell walls or things like that. But for some micronutrients, they might be found in important molecules like chlorophyll. They might assist in the production of other very important molecules within the plant. So we definitely want to make sure that our micronutrients are not ignored. When we talk about nutrients, aside from just understanding what nutrients we have and making sure that the plant is provided with all of those, we also want to pay attention to nutrient mobility. And this topic talks about how nutrients move from the point of entry. So say we are irrigating our plants with fertilizer water, those nutrients are entering our plants through our roots, but then how do they move elsewhere in the plant, and how do they sort of deposit within the plant? How are they used? Different elements are going to be translocated or move and deposit differently within the plant. And this can be broken down into two categories. We will typically talk about mobile versus immobile nutrients. Once deposited, some elements are fixed in place, so those would be considered immobile nutrients, while others can be remobilized if a deficiency starts occurring in the environment, and those would be considered mobile nutrients. And don't worry, we're going to be reinforcing this by talking about each nutrient, so you'll get a lot of examples here coming up. But being aware of deficiencies is something that people are very concerned with any crop, and in particular, cannabis. It's good to be aware of what's going on by understanding what nutrient deficiency symptoms look like and how mobility or immobility can help us identify what deficiency is present. So when we say there's a deficiency, we know because we're looking at a couple of different symptoms. The worst of this is going to be necrosis. Now that's going to be localized death of tissues. So when you see brown, crunchy, or dead leaves, we would consider that necrosis. Typically, before we get to that point, however, we see some other symptoms, for example, chlorosis, which is where our plant becomes yellow or just slightly less green. And it's caused by a loss or a reduction in the development of chlorophyll. So chlorophyll is what makes the plant green. So when we start losing chlorophyll molecules, you start to see more yellowing. And then stunted growth of stems and leaves can also be due to nutrient deficiencies and can be a little bit more subtle, more difficult to diagnose. Typically, we don't have a very hard time identifying chlorosis. So let's get into individual nutrient topics. And we'll start with nitrogen, the big one, the one that we know all plants need and need in the biggest amounts. Nitrogen would be considered a mobile nutrient. So we think back on this and what does that mean? Our mobile nutrients, once they enter the plant, if there is a deficiency, they can be remobilized. So in this case, and with most mobile nutrients, our oldest leaves are going to show deficiencies first because our plant is able to take the nitrogen from those older leaves and move it up to the younger leaves. For nitrogen in general, this is involved in building cellular components across the entire plant, including proteins and chlorophyll. But since it's not always incorporated into a structure, we are able to remobilize that. Looking at the deficiency symptoms, you can see here on the right, you really see an example of those older leaves being affected by a deficiency. So we've got these larger fan leaves down further down on the plant that are severely yellow. But then we look at the top here and we see, you know, it's pretty green. It's looking fairly healthy on the top. We know that with that older foliage being affected, that is a mobile nutrient deficiency. And in this case, we look at the overall yellow appearance, it's worse in the older leaves, and the overall stunted growth tells us that this is most likely a nitrogen deficiency. Next up, phosphorus. Phosphorus is also a mobile nutrient, and it's a major component of DNA and cell membranes. So we know that this is something else that's providing a lot of support for low-level cellular activities and also helping us with energy transport. So, you know, this is a really important one as well. It's another macronutrient and it's mobile. So again, thinking back on the mobile, with the deficiency symptoms, we tend to see things happening on the lower leaves first, but we also have some pretty key deficiency symptoms that are associated with phosphorus. Particularly with early stages of phosphorus deficiency, we tend to see dark green or purpling appearances in foliage. And we'll see smaller leaf size and just an overall reduced shoot growth that can be traced back to, you know, we're less able to transport energy throughout the plant. And so the plant is going to be overall somewhat stunted. Next up, the last of the macros, we've got potassium. And again, this is another mobile nutrient. Potassium is very important with cellular water balance, cellular nutrient balance, stomatal action, so, and cellular biochemistry activities that are going on in general. Very low level issues, very low level activities, very important in the water balance inside of the plant. And you can see with some of these deficiency symptoms, as it gets worse, we start to see some issues or some symptoms of things like tip burn, which we might expect to see in a plant that is having some water balance issues. More susceptible to water stress in general, and a blotchy appearance, again, of the older leaves first, because this is a mobile nutrient. And once we get to advanced stages, you start to see these leaves look really bad and lots of necrosis or leaf death or dead spots on those leaves. Next up, we're going to talk about some of our secondary nutrients. Now, these are important, but they're not the macros. So they're the second most used category. And calcium is going to be our first one. And it's also our first immobile nutrient. So with calcium, what we see is that calcium is a very important structural component of plant cells. So once we've incorporated calcium into our developing plant tissue, the plant is unable to sort of redeploy that calcium to other places in the plant. It's also very important for cellular membrane function, but the effects that we see with deficiencies are very much related to plant cell wall issues. And since it's an immobile nutrient, we do start to see deficiency symptoms on the younger foliage, more so than the older foliage. And in other crops, we may see tip burn that looks fairly characteristic on younger developing leaves, but in cannabis, you will see this fairly characteristic chlorotic and necrotic spots across leaves and leaf margins. Now, I've seen this, firsthand in a number of strains that have this issue, and it always ties back to calcium deficiency. For some strains, you may also see dark veins occurring, and if you were growing a fruiting crop, which we're not, but damage to fruits in fruiting crop also points back to, this developing tissue is highly susceptible to calcium deficiencies. Next up, we've got magnesium, and this takes us back to our mobile nutrients. And this is, I would say, perhaps one of the most mobile nutrients, and thankfully it's also one of the easiest nutrients to correct a deficiency in. This is a major component in the chlorophyll molecule, so you start to see yellowing very quickly if you're having magnesium issues, but you also see that the plants respond very quickly to corrections in magnesium deficiencies. So since it's a mobile nutrient, again, we are seeing the issues with deficiency symptoms on the older leaves. So look here on the right-hand side, and you'll see it starts off as an interveinal chlorosis where you can see that the veins still retain their green appearance a bit longer than the leaf margins here. And this is due to the chlorophyll in the older leaves being broken down so it can be supplied to the younger leaves as they develop. And this one, is very characteristic, and plants will respond very well to treatments for magnesium deficiencies very quickly. Finally, we've got sulfur. So this is the last of our secondary macronutrients, and it's another immobile nutrient. This is, again, very important for low-level biochemistry, low-level protein production throughout the entire plant. And since it's immobile, what we're looking at is the younger leaves will be affected first. Again, with deficiency symptoms, we start to see that it's an all-over, evenly spread chlorosis, and the plants just, from the top down, start to look more and more yellow. What I will say is with sulfur, we don't see sulfur deficiency very often because many fertilizers, and we'll talk about this a bit later on, many fertilizers have a sulfur component to them somewhere. So sulfur deficiencies are one of the least likely, but when you see them, they're fairly easy to identify. And in this case, I talked about how with magnesium, there was an interveinal chlorosis where the veins sort of retain their green color a bit longer than the margins. But with sulfur, it's all over. Everything just sort of yellows evenly. So let's summarize that really quick with mobility and the types of nutrients that we talked about. Mobile nutrients are going to show their deficiency symptoms in the lower or older leaves first. And these are going to be nutrients such as nitrogen, phosphorus, potassium, and magnesium. So all three of the macros and one of the secondaries. And with immobile nutrients, the plant can't repurpose these these nutrients that have already been deposited. So we're going to start seeing the deficiency symptoms on the youngest leaves first. And these are going to be, for the most part, are micronutrients: iron, manganese, boron, copper, zinc, molybdenum. But also, importantly, two of our secondary nutrients, calcium and sulfur. So that's our mobility summary. Moving on to a topic that many growers do get a little bit confused with: nutrient mobility. We're going to talk about nutrient availability and pH. So availability is the ease at which nutrients move out of the soil and into plants. And this is different than mobility, right? Mobility, when we talk about nutrient mobility, we're talking about what's going on inside of that plant. Whereas the availability, that's going to be referring to what are those nutrients doing outside of the plant, and can our plant absorb them? Now, this is highly effective by the media or solution pH, because you'll see on the right-hand side, this is a pretty classic nutrient pH availability chart. And one nutrient that is very, very affected by this, and also a pretty common issue, is iron. So remember I mentioned earlier that iron's a little problematic. This is why. When we talk about our media pH and being out of range or nutrient lockout, some growers might say, what we're really talking about is the media pH being a little too high or a little too low. And you can see what happens to the nutrient availability when we get outside of our ideal range. So at the bottom here, we've got a chart of pH. So it goes down to 4 pH, which is very acidic. It goes up to 10 pH, which is very basic. And each of these little bars is a different plant important nutrient and what their availability looks like within each of those ranges. So you'll see that we've got a blue highlighted here for hydroponic solutions, where we're targeting 5.5 to about 6.2 as our ideal range. And you can see where how these nutrients behave. So let's take a look at iron. When pH is low, iron is very available as the plant needs. But when we start to get above 6.2, or even above 6.5, we see this availability dropping off and dropping off until we can't get any iron anymore. So pH of your media, of your solution, is going to very much influence how well your plants are able to take up nutrients, and can be different depending on what nutrient we're talking about. When we're looking at the 5.5 to 6.2 range, this has the best availability across the spectrum, where most nutrients are mostly available. So that's typically what we're targeting there. We talked about some availability, we talked about mobility, and what are the nutrients that we care about. But where are these nutrients coming from? How do we actually get those nutrients to the plants? It's a very important question, and it's a very important piece of information for you to have when you're planning your production. So there's a couple of different strategies. There's a lot of different ways that we can get nutrients to our plants. One way that's been very common in big agriculture for a long time is utilizing fertilizer straights. Now, what this is they're typically a product that contains one type of fertilizer component. This might be something like ammonium sulfate, calcium nitrate, urea, magnesium sulfate. Those are the types of terms you'll hear when talking about fertilizer straights. And a lot of people use these in field agriculture, but some greenhouse growers can also use them, and we'll discuss this in a moment, to mix up their own fertilizer plans. Next up, we've got blended fertilizers, where you can even physically see the difference between these. Our fertilizer straights, look very uniform. There's only one type of thing in there. But with our blended fertilizers, we've got multiple fertilizer components blended into specific ratios. And this is where you start to hear people talking about those NPK ratios, for example, 15-0-15, 5-12-26, 20-20-20, things like that. We're blending multiple fertilizer strains together to get a combination that is compatible with, all the components are compatible with each other and provide expected predictable nutrition to our crops. But beyond that, and a little bit beyond the scope of this presentation, but important to acknowledge, is environmental processes. How do fertilizers become available in nature? Like, yes, we're mining those fertilizer strains, but how did they get there? There's, geologic and natural processes such as the nitrogen cycle, the phosphorus cycle, and the composting or breaking down of organic material that puts those fertilizer components back into the environment. We won't be talking about that today. We'll be talking about straights and blended fertilizers. So with the two types of fertilizers that we talk about, there's really two types of fertilizer strategies. One is relying completely on formulated blends, and the other is on-site blending from straights, going nutrient by nutrient. And there's pros and cons to each of these. With the formulated blends, we've got a lot of pros, including, there's less mixing that you have to do because you've got all of your fertilizer components in 1 or 2 bags. They come with a complete nutrient package because they've been designed to provide complete nutrition. They're great for commercial production because of the less labor required with the mixing and less calculations. And they're typically more accessible in terms of, like, you can go out and buy formulated blends from fertilizer companies. Some cons, and I would say this is a big one for some people and a nothing con for other people, is that they're less flexible. Once you buy a formulated blend, you can't really influence those ratios, but there are a lot of different blends out there, and there's probably a blend that covers your needs and your desires for your crop. So with the on-site blending from straights, the pros, this is more flexible for recipe creation. So if you have some specific nutrition targets that you want to hit and then you're experimenting with, or you have a very finicky strain that you're growing, straights might be the way to go. And they're great for research or for multiple crops because you can really tune it in. If you're having, like I said, the finicky strains, you might want to tweak things a little bit. But the cons here can be a pretty big setback. There's more labor required, more technical knowledge is required as well. And there's a higher potential for mixing errors. And what do I mean by mixing errors? One, possibly you might be mixing things too concentrated, but in general, like what people run into most commonly is that some fertilizers are not compatible to mix with others. And very classically, we want to remember with straights or with blends, we want to keep calcium fertilizers separated from phosphates or sulfates. Now, this isn't saying like, oh, you mix these two together and your fertilizer will catch on fire. No, but there are chemical processes that happen when these come into contact, and you end up with some precipitate, some solids that will fall to the bottom of your tank, that will clog your filters, and are generally just less plant available. So that's where this warning comes from. Next up, with micronutrients, when we're talking about blends or straights, many people are looking at different macronutrients that we need to consider, but micronutrients are also available either nutrient by nutrient or in blends, and they come in multiple forms. The most common are going to be sulfate forms or chelated forms that you'll hear about, and there's reasons why you might want to pick one over the other. With chelation, these are available in a wider pH range, and they tend to be a little bit more stable, less likely to interact with other fertilizers, less likely to interact with any other chemistry you might have going on, and they contain a chelating agent. With sulfate forms, these are extremely mobile while in solution or in media, and they tend to be a lot cheaper, but they're less stable and they're more likely to interact with maybe some other chemistry that's going on in your production. These tend to be better for field crops or for foliar applications, but they're also less compatible with some sanitation strategies like ozone or UV. So, you know, there's something for everyone here, and it really depends on what's going on in your production. Neither one are a bad choice. It's really just what's most appropriate for you. I mentioned a couple of times fertilizer ratios. I mentioned a couple of times NPK. So what do those mean? And you know, what are some common ones? So NPK is going to be looking at the percentages of nitrogen, phosphorus, and potassium that we have in our fertilizer, but they can also be expressed as a ratio. And you will tend to see these be the most common. So like a 1 to 1 to 1, nitrogen, phosphorus, potassium, 2 to 1 to 2, 1 to 3 to 2, 3 to 1 to 3. And I would say that, you know, think back about what I said about the blends. You'll see things like 20, 20, 20, which could be simplified as a 1 to 1 to 1. You'll see things like 5, 12, 26, which could be expressed as a 1, 2, 3. So, you know, that's when we're talking about ratios, we are simplifying those percentages. But we also have some targets, and when we're thinking about cannabis in general, what are some reasonable ratios? And let's talk about, you know, specifically some ratios. The nitrogen to phosphorus ratios, we're typically looking for 1 to 1, 2 to 1, or 3 to 1. And recent research is really showing us that less phosphorus is completely sufficient. So we really want to end up in the 2 to 1 or 3 to 1 ratio. Nitrogen to potassium ratios, oftentimes we're looking for a 1 to 1 or a 1 to 2 ratio when it comes to cannabis. We know that cannabis is a flowering crop, and many flowering crops benefit from a little additional potassium. But at the very least, we want to supply our nitrogen and our potassium in equal amounts. And then importantly, another one is calcium and magnesium, which is not included in our typical NPK ratios, but you can find it on some fertilizer bags, which we'll talk about. And for cannabis, importantly, we're looking at ratios of 2 to 1 or 3 to 1 calcium to magnesium. More calcium being twice as much or 3 times as much calcium as magnesium being in the fertilizer plan. Another important component of fertilizers that you may hear talked about or you will see written on bags is acid and basic forming tendencies. We know that fertilizers can alter the pH of your growing media, but how is that happening? Typically, what's happening is it's dependent on nitrogen form. So the pH of our fertilizer solution, say if you're to just mix up a bunch of fertilizers in your stock tank and take a pH reading, this does not relate to our acid or basic forming tendency of a fertilizer. That is not going to have an effect on what's happening in our media, like a peat-based or a soil-based media. So what is happening here is that ammoniacal nitrogen, that's going to be our NH4 nitrogen, is one form of nitrogen fertilizer that's very commonly used in our fertilizers. And this tends to lead to an acid forming reaction. When the plant takes up one molecule of ammoniacal nitrogen at the root zone, it releases a hydrogen molecule. And then the same thing can be said about our nitrogen, nitrate nitrogen, which is very basic forming. When our plant takes up one molecule of nitrate, it releases a hydroxide molecule, or OH. This leads to more basic environment in our media. And this is a really complicated topic. You know, I could spend quite a while talking about the chemistry of this, but understanding that ammoniacal nitrogen leads to acid forming and nitrate nitrogen leads to basic forming, that's really all you need to know to make some, to draw some inferences about your fertilizer. Again, on the topic of pH management, another thing that can have significant effects on your pH in your media is alkalinity. So what do we do when we want to control alkalinity, and what is it? What's going on there? Water quality is where we're going to see our alkalinity measurements. And I just want to clarify really quick, because there is a little bit of a vocabulary issue here that can be very confusing. When we're talking about the pH scale, as you see down here at the bottom, we've got acidic in the 0 to 6 range, we've got neutral at 7, and then we've got alkaline or basic conditions at 8 to 14. So when we're talking about alkaline, this is a liquid or a media with a pH above 7. But when we're talking about alkalinity, this is the capacity of water to resist acidification, and it's measured a different way. So in ppm, calcium carbonate, or millieqs per liter of calcium carbonate. So we definitely don't want to get these two words confused. Alkalinity often comes from dissolved calcium or magnesium carbonate in our tap water, in our base water, well water. And the pH of media such as peat, field soil, things like that, they're going to be determined by deposition of alkalinity over time. So when you irrigate with a water with a high alkalinity, you tend to deposit those calcium carbonate or other calcium and magnesium compounds into your media. So when we are looking at the peat in the field soil, we really want to think about alkalinity. But when we're talking about hydroponic medias, such as rock wool or cocoa coir are some really common ones, they're less impacted by the alkalinity, and they're more going to be determined by the pH of your fertigation water. So if you're growing in peat and you're growing in soil, you are going to want to deal with this alkalinity. So how do we do that? Typically, we recommend that alkalinity be mitigated through the addition of acids. And here at Griffin, at GGS Pro, we typically recommend sulfuric acid because it has the least amount of impact on your fertility plan. It is a strong acid, and it's going to be most cost effective in the face of a high starting alkalinity. But something to remember is that it is not OMRI approved, unfortunately. And this isn't an issue for a lot of growers, but some people do try to follow organic principles. And if you're trying to do that and you have a poor starting water quality or something that has a high alkalinity, it's going to be really hard for you to deal with. Weak acids such as citric acids can be used and are OMRI approved, but you're going to start to have a lot of problems over time, and you're going to go through a lot of citric acid. Another component with citric acid is that it does encourage microbial growth. And like I said, more product is typically required. So when we're talking about alkalinity, here are some common values that you will see that we consider medium to high to kind of extreme. Low alkalinity water would be measured in the range of 0 to about 40 ppm. So 40 to about 100 ppm calcium carbonate is going to be medium. And then when we start to get to 150, 200, 250, 300, this is where we really do need to look at some treatment to mitigate that alkalinity issue over time. And you'll see that it really doesn't take a whole lot of sulfuric acid when you're using a highly concentrated version. We recommend 93%. But this is, 0.75 ounces per 100 gallon to mitigate that alkalinity. It doesn't take a lot. So those are that is one strategy that we highly recommend. And overall, when we're talking about water quality, here are some other important components that you want to keep an eye on. We talked about alkalinity, and if it gets over 300 ppm, calcium carbonate equivalent, we really want to talk about utilizing another water source. For EC, EC is electrical conductivity. We really don't want to see anything over 1.5 on our base water. But for some crops, it's going to be even lower, 0.7. For pH, with our starting crop or with our starting water, that's going to be heavily dependent on fertilizer, alkalinity, our acid injection. But we're looking for, in general for agriculture, 5.2 to 6.2. But for cannabis, we're looking for 5.8 to 6.2, a little bit higher. And then looking at the initial components of what fertilizer salts might be present in our water. We want to pay attention to things like calcium and magnesium. Do we have too much iron? Are there a lot of micronutrients? Is there anything else in there that we might want to pay attention to? And when we have really poor starting water quality, a lot of growers will turn to RO, or reverse osmosis water. However, if you think back to what we were looking at the previous slide, we don't really, we can deal with a lot of conditions. Most operations do not require RO water. The primary need for RO water is going to be with high EC irrigation water. And again, if we're seeing really pure water, it's going to be from 0 to 10 ppm alkalinity, typically 7 pH, free from fertilizer salts, but no buffering capacity, so no ability to resist change to pH. RO water can swing dramatically in terms of pH conditions in response to fertilizer addition. And our best practices there are adding a little bit of buffering capacity back with potassium bicarbonate. Next up, we've got reading fertilizer labels. Now, this is going to be a really practical skill for you to have, just understanding all of that information that's on the bag. And I've got an example here from J.R. Peters, which is the JAX 51226 Part A. We're going to go through this piece by piece. So first off, we've got that NPK we've been talking about. What's in the bag? These are our main percentages of nitrogen, phosphate, and potash. So that's the 51226 NPK. We've also got our guaranteed analysis, which is a detailed breakdown of each element contained. And then we will also often have a derived from statement, which talks about those fertilizer traits that were used to produce this product. Going from there, we have some additional important properties, the potential acidity and basicity, like we talked about earlier. Is this an acid forming or basic forming? And then oftentimes we will have a statement of what is the EC of this product when we make up a certain concentration in parts per million nitrogen for the solution. And what JAX has also provided, you won't find this on many bags, but some fertilizers do. They've also provided the parts per million breakdown of the rest of the elements when you're at that concentration. And a good fertilizer bag will also have how to use it, your suggested feeding recipes, and it should include something like a statement on the parts per million nitrogen, like we talked about, the EC at that solution so you can measure it, and weight information for mixing up a 100-gallon solution. All right, let's just take a closer look really quick at some of the more subtle information that derived from the potential basicity or acidity, but in this case it's basic, and the limit of solubility. So a quality fertilizer where we've got a transparency in production, we've got consistency in production, they will have this information from you. They will be able to tell you, what did we make our fertilizer from? They'll be able to tell you, how does this fertilizer affect our media? Is it potentially acidic or basic? And they will be able to tell you what you can expect when you're trying to dissolve your fertilizer. How much is too much? What do you want to stay below? This is very important information to have. And quality fertilizers provided right on the bag. So I've talked about EC and ppm a couple of times. So let's just clarify quickly, what is that? So EC is electrical conductivity, and this is a measure of how well water conducts electricity influenced by total dissolved solids or salts. It's typically measured in millisiemens per centimeter, and an example would be like 2.1 millisiemens. Whereas parts per million, this can be used in a lot of scenarios, and this is simply a count of particles present in every 1 million particles. The specificity depends on the measurement of calculation, and you probably heard me say this a couple of times already, 200 parts per million nitrogen. So that's something that we talk about a lot in horticulture, is looking at parts per million nitrogen. Whereas you will hear a lot of people talk about like, oh, we're making up a 1000 ppm solution. And what they're talking about is total salts there. Whereas when you're looking at the fertilizer bag, or when you're talking in horticultural terms, we tend to talk about this, we frame it in parts per million nitrogen alone, nothing else. So why do we care about this? For EC, we're measuring the total amount of dissolved solids without any differentiation. This is going back to like, the TDS, like what is our total solution? EC sensors are relatively simple and inexpensive. So if you're trying to look at, are you mixing up your fertilizer properly? EC is a really great way to test that out. And expected EC can be calculated based on fertilizer added. So you go back to your bag of fertilizer and you see, oh, we've got a 1.0 EC when we mix it up at 50 ppm nitrogen. And you mix that up and you go test it with your EC meter, and you can tell if you've done it correctly or not. Whereas with our parts per million nitrogen, this is an individual element concentration. And we're often looking in horticulture at feed rate recommendations that talk about parts per million nitrogen. Since nitrogen is the most needed plant nutrient, knowing parts per million nitrogen gives us an idea of how effective a feed will be. But in contrast with EC, we can't measure this directly. Then how? Again, that goes back into the measurement. Calculating based on fertilizer properties, as we said, reading our EC meters, measuring a physical quality of the solution. This is very straightforward. And we usually can convert to total dissolved solids, which is similar to parts per million, but I would honestly stay away from that. I would just stick with using EC when we're target checking. And then with our parts per million nitrogen, if we want to measure this, like I said, we can't really measure this directly with a handheld meter. We can calculate it based off of our fertilizer weights. We can measure it directly through water testing. So if you take a sample and send it to a lab, they will be able to tell you how much nitrogen is in there. One thing to note is that mixing blended fertilizers and measuring EC alone will not tell us parts per million nitrogen unless we do all of these calculations that we just talked about. The only thing you can measure directly in that scenario is our EC, and that's going to talk about our total with all of our nutrients. So typical values, starting water quality, we talked about 0 to 0.5 millisiemens. We've got a lot of room left for fertilizer. At 0.5 to 1.1, we don't really have much room left. And then, 1.1 to 2.5, if we're talking about water we've already added fertilizer to, this is a good range. 1 is pretty low if we're talking about fertilizer water, and 2.5 is pretty high. I've seen people feed it higher, but we really don't want to go over 2.5 for general use. With nitrogen, we typically frame this in light, medium, or heavy feeders. So light feeders are looking for a 50 to 100 ppm nitrogen level. This is seedlings, clones, and other low nutrient requirement crops. Medium feeders are going to be 100 to 150 parts per million nitrogen. Heavy feeders are going to be up to 250 ppm nitrogen. And sometimes in agriculture, horticulture, we do use corrective feeding, where we feed a little bit higher temporarily to treat underfed crops at 250 to 300 ppm nitrogen. 350 plus ppm nitrogen is generally considered too high. You run the risk of burning your crops. So just to visualize that for you, different crops have different fertilizer needs. Here's the clones, the seedlings, our light feeders. We ramp it up a bit with our young plants, our microgreens, radishes, leafy greens. And then we find cannabis in the heavy feeder category, between 150 to 250 ppm nitrogen, alongside things like tomatoes, peppers, and eggplants. So putting it all together for cannabis nutrition. Cannabis needs nutrition just like any other crop. And cannabis nutrition needs can be met by many different fertilizer strategies. This is not a one size fits all. You know, it's going to be dependent on your equipment, the strain you're growing, your personal experience on what you've worked with before. And you really, you can make it work with any combination of factors. It's really dependent on you, your experience, your equipment, and your preference. So just to give you some concrete cannabis nutrition targets as well, with veg and moms, we typically break this down into, you know, NPK. We're looking at our secondaries as well, and then EC and pH. Veg and moms, early veg, we would typically feed, you know, like 100 ppm nitrogen, up to 200 parts per million nitrogen, depending on how much growth you're trying to drive. Phosphorus, fairly low. Potassium, again, this is a flowering crop. We want to keep it at least equal to the nitrogen when we're in veg, when we're in mom stage. And then calcium, cannabis loves calcium. So we want to make sure we're providing sufficient calcium there at 100 parts per million or higher. With magnesium, again, this is going to be dependent on the calcium. We're thinking back to those ratios. We want to know how much calcium we're providing and target our magnesium based on that. With EC, again, this is going to depend on fertilizer, but 1.0 to 2.5 is typically going to be a good range, and pH doesn't change depending on what stage you're in. We're always looking for 5.8 to 6.2. For flour, there's only a couple of differences. Oftentimes, we're going to end up with a bit higher nitrogen in some stages, some areas, especially with early flower, when we're still trying to drive a lot of growth. And then with our EC, we tend to want to have a bit of a lower EC at near the end, but again, it's going to depend on our fertilizer. And finding a quality fertilizer. We talked about how to read bags and understand what you're seeing, but you know, many quality fertilizers exist in the horticulture space, agriculture space, and there's a lot of products out there. So what are you looking for to know that you've got a quality fertilizer? Any really high quality fertilizer should have a physical consistency of the product here. You know, they're not all going to be blue, but we shouldn't be seeing large chunks. We shouldn't be seeing any debris in there. It should be consistent, and we should have a clarity of formulation. You should understand what's in there, what exactly the nutrients are that you're providing. There should be informative labels like we discussed, and we should have a solid supply chain where we know that we're not going to have an interruption in the availability of our products. Horticulturally sound products can be used for many crops. So you might use a cannabis specific fertilizer. You might use just a general horticulture fertilizer that someone might use for pansies or tomatoes or what have you. As long as you're providing complete nutrition, you can, you know, use the tools that you have on hand. Additionally, you know, quality that you can see should really come through in your fertilizer. How do you evaluate that on site? There's a couple of things you can do. Solubility and turbidity are key indicators of quality fertilizer inputs. So solubility is the ability to completely dissolve in solution, and being aware of that limit of solubility like we saw on that Jack's bag. And then turbidity is the clarity or cloudiness of a solution once dissolved. And there's an example here on the right-hand side where we've conducted a jar test to check for the solubility and turbidity, where we can see on the right-hand side, this is very cloudy. There's a whitish color in there. We really can't see through it. But on the left-hand side, we see that this is a very clear solution. Color may or may not come into it, but is usually not a quality indicator. Some fertilizers can be somewhat yellow if they have iron added. Some fertilizers add that blue dye, and some do not. So what we're really looking for are no sediments, no cloudiness, and things like that. Clear solutions bring highly soluble inputs to the crop. And if you're ever curious, perform a jar test for that quality, solubility, and compatibility. And when it comes to Griffin, we do have a number of different fertilizer products from a number of different producers. Our favorites to work with are going to be the Master Plant Prod, the Jax Nutrients, but we've also got some products from Yara and other suppliers. Some that are, as I said, cannabis specific, and some that are just generally good fertilizers. You've got a lot of choices here for what to put on your products, and Griffin can help you make those choices as well. All right, so if you have any questions, feel free to ask them now, and if you think of any later, always feel free to reach out to your Griffin sales rep for help, or Griffin's GGS Pro department. All right, thank you. That's all I've got.
Thank you, Erica. I don't see any questions coming through. I can unmute everybody if they'd like.
Why don't we, if folks have a question, let's have them put it into the chat panel.
Okay.
And then if we have a need for more detailed conversation, we can dig into that.
Sure.
Erica, thank you so much. This was a great overview, starting at the basics and getting all the way to the end. It's also important for our attendees to understand that GGS Pro builds customized fertilizer programs. So Erica talked about water quality and balancing pH in your media or in your solution, depending on what you're growing in. GGS Pro will start with your water quality, understand your media and your crop plan, and they will build a fertilizer program customized to you and your situation, the number of injector sites, things like that. So they do a great job with this. It's a wonderful service, and it's something that I hope everybody's able to take advantage of.
I do have one question that came in. Fred Ruckle said, great presentation, best one by Griffin so far about cannabis. So that was Fred Ruckle from OK Grow.
Thank you so much.
Good. So for everybody on the call, we will get you a handout from the presentation from Erica today. You'll see that coming to you from Scott Baker. And we thank you for your attendance and look forward to working with you.
All right, thanks everybody.